Hydrogen fuel cells represent a distinct class of energy conversion devices. They operate as electrochemical systems, fundamentally differing from internal combustion engines or traditional batteries. Their primary function is to convert chemical energy directly into electrical energy. This conversion process is achieved without combustion, meaning there are no flames, sparks, or internal energy storage mechanisms typical of engines or batteries. Instead, a continuous flow of reactants sustains the power generation. Fuel cells offer several compelling advantages. They boast high efficiencies, often exceeding those of traditional power generation methods. Their operation is remarkably quiet, contributing to their appeal in various applications. Furthermore, fuel cells provide continuous power generation, a critical capability as long as the necessary fuel and oxygen are supplied. This makes them ideal for applications requiring uninterrupted energy. Distinguishing fuel cells from other technologies is crucial. Unlike engines, they produce no noise, vibration, or mechanical wear, significantly reducing maintenance needs. In contrast to batteries, fuel cells do not require a charging cycle. They continuously convert chemical energy, providing a steady power output, rather than storing a finite amount of energy. At its heart, a hydrogen fuel cell operates on a straightforward electrochemical principle. It facilitates a controlled reaction between hydrogen and oxygen, producing electricity. This process avoids direct combustion, leading to cleaner and more efficient energy production. The mechanism begins at the anode, where hydrogen molecules are introduced. A catalyst splits these molecules, separating electrons from protons. The protons then pass through a selective electrolyte membrane. The freed electrons, unable to pass through the electrolyte, are forced to travel through an external electrical circuit. This movement of electrons constitutes the electrical current, performing useful electrical work. At the cathode, these electrons, along with the protons that have crossed the electrolyte, combine with oxygen from the air. This recombination forms water, the primary byproduct of the reaction. The outputs of this elegant process are electricity, usable heat, and pure water. This makes fuel cells a remarkably clean power source, especially when the hydrogen itself is produced renewably. The benefits of this non-combustion approach are significant. It allows for exceptionally quiet operation, suitable for noise-sensitive environments. Non-combustion also leads to inherently higher efficiencies, particularly at smaller scales, where thermodynamic losses are minimized. A fundamental advantage for uptime is the continuous power production, ensuring consistent energy supply. Fuel cells are not a monolithic technology, but rather a family of diverse systems. Each type is specifically designed to operate under different temperatures, utilize various fuels, and cater to distinct use cases. This adaptability highlights their nature as a platform technology. One prominent type is the proton exchange membrane, or PEM, fuel cell. These cells operate at relatively low temperatures, typically below 100 degrees Celsius. They are known for their quick response times and dynamic power adjustment capabilities. PEM fuel cells are particularly well suited for mobile applications, such as automotive vehicles and portable electronics. However, they require exceptionally strict fuel purity to prevent catalyst poisoning and ensure longevity. Another significant variant is the solid oxide fuel cell, or SOFC. These cells operate at very high temperatures, often hundreds of degrees Celsius. Their high operating temperature allows for greater fuel flexibility. SOFCs can utilize hydrogen, natural gas, ammonia, or even biogas directly. They are ideally suited for large-scale industrial and stationary power generation, especially where waste heat capture can be integrated for combined heat and power systems. A trade-off for SOFCs is their slower startup time and the complexity of their thermal management systems due to the high operating temperatures. Despite this, their efficiency and fuel versatility are major advantages. Beyond PEM and SOFC, other types include alkaline fuel cells, phosphoric acid fuel cells, and molten carbonate fuel cells. Each of these possesses specific trade-offs concerning performance, cost, and operating conditions, making them suitable for niche applications. This broad spectrum underscores that fuel cells represent a platform technology. There isn't a single best fuel cell, but rather a tailored solution for a specific energy challenge and operational environment. At the heart of any fuel cell system lies the fuel cell stack. This component comprises multiple individual cells layered together in series, generating a usable voltage and power output. Each cell contributes a small voltage, and stacking them increases the total system voltage. Within each individual cell are several critical components. These include the electrolyte or membrane, catalyst layers, bipolar plates, and seals. The electrolyte facilitates proton transfer, while the catalyst layers accelerate the electrochemical reactions. The bipolar plates serve multiple functions, including distributing reactants, collecting current, and managing heat. The design and material selection of these components significantly influence the power density, efficiency, and degradation behavior of the entire stack. Beyond the stack, the balance of plant, or BOP, encompasses all the supporting systems necessary for the stack's safe and efficient operation. These auxiliary components are vital for system functionality. The BOP includes subsystems for hydrogen delivery, air management for oxygen supply, and humidification to maintain membrane performance. Cooling systems are essential for thermal regulation, alongside pumps, power electronics for conditioning the electrical output, and various sensors. A sophisticated control software orchestrates the entire BOP, ensuring optimal performance and safety. This integrated system manages reactant flow, temperature, and electrical output precisely. The reliability of a fuel cell system is heavily dependent on the BOP. In fact, most real-world failures and maintenance issues often originate not in the stack itself, but within these supporting systems. This emphasizes that fuel cell engineering is fundamentally about systems integration. The stack is critical, but its performance is intrinsically linked to the meticulous design and robust operation of the entire balance of plant. The fuel for a hydrogen fuel cell is, of course, hydrogen, but its production methods vary widely. These methods significantly impact the cost, purity, availability, and most importantly, the carbon intensity of the hydrogen. Understanding these distinctions is crucial. Green hydrogen is produced through electrolysis, powered entirely by renewable electricity sources such as solar or wind. This method offers the lowest carbon emissions, but currently comes with a higher production cost. It is often seen as the ultimate sustainable solution. Blue hydrogen is derived from fossil fuels, typically natural gas, with the critical addition of carbon capture and storage technologies. While it reduces emissions compared to traditional methods, its environmental footprint is still subject to the effectiveness and permanence of carbon capture. Gray hydrogen, the most common production method today, also uses fossil fuels, primarily natural gas, through a process called steam methane reforming. However, it releases carbon dioxide directly into the atmosphere, making it a high carbon intensity fuel. Beyond pure hydrogen, fuel cells can also operate on alternative fuels through a process called reforming. Methanol, ammonia, natural gas, and even biogas can be converted to hydrogen on board or at a fueling station. Utilizing alternative fuels expands the potential deployment options for fuel cells, especially in regions without a developed hydrogen infrastructure. However, this approach adds complexity to the system. Reforming processes introduce additional equipment, leading to energy losses during conversion, and can still generate emissions. This approach ties fuel cell viability to upstream energy markets and existing infrastructure for these feedstocks. The choice of fuel deeply influences the overall environmental impact and economic viability of a fuel cell application. It necessitates a holistic assessment from source to end use. To evaluate and compare fuel cell systems, several key performance indicators are employed. These metrics provide a comprehensive understanding of a system's capabilities and limitations. Primary indicators include efficiency, which measures the electrical output relative to the energy input of the fuel. Power density indicates the power generated per unit volume or weight, crucial for mobile applications. Durability and lifetime are paramount, reflecting how long a fuel cell system can operate reliably before needing significant maintenance or replacement. Cold start capability, the ability to begin operation in freezing temperatures, is vital for many climates. Load following capability, or the ability to quickly adjust power output in response to changing demand, is another important metric. There often remains a gap between laboratory-tested performance and real-world operational results. Fuel cells are remarkably versatile, finding diverse applications across multiple sectors. In transportation, they are increasingly powering heavy-duty trucks, buses, and trains. These vehicles benefit from their long-range, fast refueling times and high payload capacities. For stationary power, fuel cells serve as reliable backup power sources, especially for critical infrastructure. They are also integral to microgrids and distributed generation schemes, providing clean, quiet, and on-site electricity. Industrial settings leverage fuel cells for combined heat and power systems, maximizing energy utilization. They also offer robust solutions for off-grid operations where traditional power infrastructure is unavailable. Portable applications include power for military equipment, telecommunications towers, and remote sensing devices. Their quiet operation and energy density make them superior to conventional generators in many of these roles. The widespread adoption of hydrogen fuel cells is intrinsically linked to the development of robust infrastructure. This infrastructure is a complex ecosystem supporting the entire hydrogen value chain. Key requirements include large-scale hydrogen production facilities, efficient storage solutions for both gaseous and liquid hydrogen, and advanced compression technologies. Pipelines are essential for long-distance transport, and a network of refueling stations is critical for mobile applications. The availability and accessibility of this infrastructure have a significant impact on the deployment rate and scalability of fuel cell technologies. Building out this network represents a substantial investment. Economic considerations are central to the commercial viability of fuel cells. These include the upfront capital costs of the fuel cell stack, the balance of plant, and the installation process. Initial capital expenditure can be higher than conventional alternatives. Operating costs are another critical factor, encompassing the cost of hydrogen fuel, routine maintenance, and the eventual replacement of the fuel cell stack. Fuel costs, in particular, fluctuate based on production methods and market dynamics. A crucial determinant of economic success is the utilization rate of the fuel cell system. A high utilization rate allows the significant capital cost to be amortized over a greater volume of energy produced, improving the overall financial return. Understanding and managing these economic and infrastructure factors is as important as the technological advancements themselves. They dictate the pace and scope of fuel cell market penetration. Hydrogen fuel cells offer a compelling array of advantages. They provide high energy conversion efficiency, often surpassing that of internal combustion engines. They produce zero local emissions, contributing to cleaner air in urban environments. Their operation is remarkably quiet, making them ideal for noise-sensitive applications and urban deployments. Furthermore, their modular design allows for scalable power generation from watts to megawatts. Despite these benefits, several significant challenges persist. The high cost of producing green hydrogen remains a barrier, impacting the overall operating economics. Durability issues, particularly under real-world operating conditions involving varying loads and temperatures, continue to be an area of active research and development. The lack of comprehensive hydrogen infrastructure presents a chicken-and-egg problem for widespread adoption. The inherent complexity of integrating the fuel cell stack with its numerous balance of plant components also adds to engineering and maintenance challenges. System complexity requires sophisticated control and diagnostic systems. In the competitive energy landscape, fuel cells coexist with other technologies. These include advanced batteries for energy storage, efficient gas turbines for large-scale power generation, and synthetic fuels for liquid fuel applications. Fuel cells are poised to fill specific niches where their unique advantages are most pronounced. Looking to the future, several exciting trends are emerging. Research is focused on developing platinum-free catalysts to reduce material costs and reliance on precious metals. Higher temperature PM fuel cells are being explored for enhanced efficiency and fuel flexibility. The integration of ammonia as a hydrogen carrier is gaining traction, simplifying fuel logistics and storage. Artificial intelligence-based control systems are being developed to optimize performance, predict maintenance, and enhance reliability. Hybrid systems combining fuel cells with batteries or electrolyzers are also becoming more common. These configurations leverage the strengths of each technology for improved efficiency and flexibility. Ultimately, the success of hydrogen fuel cells depends on a holistic approach. This includes advancements in chemistry and materials science, robust engineering and systems integration, strategic infrastructure development, sound economic models, and high utilization rates. The key takeaway is that fuel cells are not merely a piece of technology. They are part of an entire supporting system. Their true potential is realized only when considering the full value chain from hydrogen production to end-use application.